Electromagnetic Theory Introduction. Electrostatics. Coulomb's Law. FAB equal to 1 divided by 4 pi epsilon naught into Q of A, Q of B, R1 divided by R2, R square. QA and QB are same sign, FAB repulsive. Different sign, FAB attractive. Applied to point charges situated in vacuum. Applied in dielectrics and conductors. Epsilon naught equal to 8.854 into 10 to the power minus 12 c square n power minus 1 m square or farad per meter. 1 pi 4 pi epsilon naught equal to 9 into 10 power 9 nm square c power minus 1. Epsilon equal to epsilon or epsilon naught. Electric field intensity E of A equal to F suffix AB divided by Q of B equal to Q of A R1 divided by 4 pi epsilon naught R square. Unit volt per meter. Electric field. If a charge of a Q coulomb is replaced at a point and a force F Newton is experienced, then the electric field E equal to F divided by Q unit Newton per coulomb or volt per meter. Principle of superposition. If the electric field is produced by more than one charge distribution, each one produces its own field and the resultant E is simply the vector sum of the individual keys. E equal to 1 divided by 4 pi epsilon naught integral value of rho r1 divided by r square d tau dash. Rho electric density R1 unit vector pointing from the source point to the field point or distance between these 2 points d tau dash element of volume dx dash dy dash dz dash. Electric potential. Consider a test point charge q dash that can be moved about an electric field. The work W required to move it at a constant speed from a point P1 to a point P2 along the given path. W equal to minus of integral value limit varies from P1 to P2 E Q dash dl minus sign shows work done against the field. Coulomb's force is a central force. If the electric field is produced not by a single point charge Q but by some fixed charge distribution. For any distribution of fixed charges, integral of EDL equal to 0, it is conservative. Unit volt, it will be equal to joules per coulomb. B equal to integral value of Q divided by 4 pi epsilon naught dr divided by r square. The principle of superposition applies to the electric potential V as well as to the electric field intensity E. Electric field outside the electrically charged body. Gauss law, which is a consequence of Coulomb's law. Capacitance coulombs per volt or farad. Electric static field is conservative. Gauss law follows from Coulomb's law. It can be stated in integral or differential form. When the charge density is 0, electric field produced by simple charge distribution can be calculated in 4 ways. By evaluating dE for an element of charge and integrating over the complete charge distribution, by calculating V in the same manner and then calculating its gradient. By integrating Poisson and Laplace equation, by using Gauss law, Coulomb's law gives potential and Gauss law, then Poisson distribution, Laplace equation. The principle of superposition gives potential, then Gauss law, Poisson distribution, Laplace equation. The potential energy associated with the charge distribution W equal to 1 by 2 integral value of B into rho d tau. Energy density epsilon naught E square divided by 2 to every point in space leads correct potential energy for whole charge distribution. Gauss law. The total electric flux of charge field E over any closed surface is equal to 1 by epsilon naught times the total net charge enclosed by the surface. Pi equal to integral of E ds cos theta equal to Q divided by epsilon naught. Applications of Gauss law. Electric field due to an infinite plane sheet of charge. Electric field due to the parallel sheet of charge. The field due to two sheets will be equal in magnitude and have same direction. The result field at E equal to E1 plus E2 equal to Q divided by epsilon naught. The field will be equal in magnitude and opposite in direction. By Artsawat law, P of A equal to mu naught IA divided by 4 pi integral value of dIA into R1 divided by R square. R1 unit vector, magnetic induction Tesla or Weber per meter square. 1 Tesla equal to 1 Weber per meter square equal to 10 power 4 Gauss. 1 Weber equal to volt per second. D of equal to IDL into B. If the current I is distributed in space with the current density JF unit equal to A ampere per meter square. P equal to mu naught divided by 4 pi integral value of JF multiplied by R1 d tau dash divided by R square. I becomes JF dA must be put under the integral sign. JF dA dl can be written as JF d tau element of volume. Ampere circular law. Integrating the normal component of del cross B over an arbitrary surface S, integral value of del cross B into dA equal to mu naught integral value of JF into dA. Then using Stokes theorem we can transform the left side of this equation into a line integral around the closed path which bounds the surface S, and integral value of BDL equal to mu naught integral value of JF dA equal to mu naught I. Using Ampere circular law to calculate B when it is constant along the path of integration. This is similar to Gauss law, which is compute E and where E is constant over the surface. Magnetic force acting on a charge Q moving with the velocity V in a magnetic field B. Q of E into B. If there is an electric field E, the total force Q within bracket E plus B into B, which is Lorentz force. For continuous current distribution, the magnetic dipole moment is M equal to 1 divided by 2 integral value of R into JF into d tau. Electromagnetic induction. An electrostatic field is a conservative integral value of EDL equal to 0. Let us consider a simple path having the shape of a loop. Then if pi is magnetic flux linking the loop, integral value of EDL equal to minus d by pi dt. The negative sign indicates that the induced electromotance tends to oppose the change in flux, which is Lenz's law. In differential form, Faraday's induction law becomes del cross E equal to minus of dou B by dou T. Neumann's equation. M suffix AB equal to mu naught divided by 4 pi integral double integral d of LA into d of LB divided by R. The general expression for the electric field intensity E equal to minus of dA by dt into del V. The energy stored in a magnetic field is equal to that required to establish the field, and the energy supplied to an element of volume d tau of conductor per unit time. dW by dt equal to integral value of dou A divided by dou T JF d tau. If there are no magnetic materials present and del cross B equal to mu naught JF is applicable. W equal to 1 by 2 mu naught integral value of B square d tau. W equal to 1 by 2 I pi. Magnetic torque is given by dW divided by d theta I. Retarded potential. If we have charge and current distributions rho j and jf in a vacuum, V equal to 1 divided by 4 by epsilon naught integral value of rho f j c divided by r into d tau. A equal to mu naught divided by 4 pi integral value of j f c divided by r into d tau, where the brackets indicates the charge. The current distributions are those at the previous time t minus r divided by c. These are the retarded potential. The square brackets will be used exclusively to identify retarded values of charge density, current density, positions, velocity, etc. Dispersion. The material media, the velocity of electromagnetic waves depends on the frequency. This phenomenon is dispersion. Retardation can be either important or negligible depending on the magnitude of the time delay, on the nature of the phenomenon involved, and on the time resolution required. Lorentz condition del A plus epsilon naught mu epsilon mu dou v by dou t equal to 0. Radiation resistance power P radiated P equal to c pi square I m square di square divided by lambda pi divided by 2 integral value of cos square theta into d theta, or P equal to 4 within bracket c pi square I square divided by 3 lambda square into di square. Radiation resistance of an elementary antenna equal to 80 pi square di divided by lambda square, which will be equal to 320 I square lambda square. Halfway plate equal to, its value will be 80 ohm. For quarter wave antenna, value will be 40 ohm. Poisson's equation. Gauss theorem in differential form. Div E equal to rho divided by epsilon r. In purely electric static field, E equal to minus grade pi. Divergence of grade pi equal to minus rho divided by epsilon naught. Del pi equal to minus rho divided by epsilon naught. Poisson equation, the operator del equal to del square is Laplacian in charge free region. Rho equal to 0. Del square pi equal to 0. It is Laplace equation. Maxwell's equation, the differential form of Gauss law in electrostatics, del dot D equal to rho or div D equal to rho. Differential form of Gauss law in magnetostatics, del dot B equal to 0 or divergence B equal to 0. Differential form of Faraday's law of electromagnetic induction, del cross E equal to minus dou B by dou T or curl E equal to minus dou B by dou T. Maxwell's modification of Ampere's law, del cross H is equal to J plus dou D by dou T. Above the equation, the notation have the following meanings. Electric field D equal to dielectric displacement, unit C by m square or coulomb per meter square. Rho charge density, unit coulomb per meter square. E electric field intensity, volt per meter. Magnetic field, P magnetic induction, Weber per meter square. H magnetic field intensity, ampere per meter. Physical significance of Maxwell's equation, del dot rho equal to del dot D equal to rho. Gauss law, integral value of D dot ds equal to integral value of rho into dv. The net outward flux of electric displacement vector through the surface enclosing a volume is equal to the net charge contained within that volume. 2. Del dot B equal to 0, integral value of B dot ds equal to 0. The net outward flux of magnetic induction B through any closed surface is equal to 0. Del cross E equal to minus dou B by dou T. Integral value of del cross E dot ds is equal to minus integral value of dou V by dou T into ds. The electromotive force around a closed path is equal to negative rate of change of magnetic flux linked with path. Fourth, del cross H is equal to J plus dou D by dou T equal to integral value of J plus dou rho by dou E into ds. The magnetomotive force around a closed path is equal to the conduction current plus V displacement current through any surface bounded by the path. Pointing theorem, d by dt of integral value of 1 by 2 within bracket E dot d plus H dot B into dv. u suffix e equal to 1 by 2 integral value of ed dot dv electrostatic potential energy in volume v. U suffix m equal to 1 by 2 integral value of h dot b into dv magnetic energy in volume v. Obviously u equal to 1 by 2 integral value of E dot D plus H dot B into dV, integral value of E cross H into ds. The vector E cross H is known as the Poynting vector. S is equal to E cross H, energy per unit time per unit area. J dot E minus equal to dou U divided by dou T plus del dot S. This is the conservation of energy in electromagnetism and is known as Poynting theorem. Radiation of oscillating dipole 1 p equal to 1 divided by 4 pi epsilon naught closing bracket p naught square omega power 4 divided by 3c cube. The total energy radiated by oscillating dipole is proportional to fourth power of the frequency. Electromagnetic waves transmitted by antenna. Electric dipole radiators are the emissions of radiation by excited atoms. Questions and answers will be continued in next presentation. Thank you. Please subscribe for the continuous presentation and your success.